In part B, we will add strong base sodium hydroxide to this mixed solution of strong acid and weak acid. Because strong acid, hydrochloric acid, will dissociate completely as 100%, and the weak acid, cyanic acid, will dissociate a tiny bit, as we saw in part A. To simplify the thinking process, we can assume that the strong base, sodium hydroxide, when titrated into this mixed solution, it will react with the strong acid first. Only after the strong acid being consumed completely, the added base will start reacting with the weak acid. Now, we'll need to figure out how much more exists in the mixed solution. Based on the concentration and the volume of the solution, we know that in the original solution, we have hydrochloric acid, HCl, 0.0100 mole initially, and cyanic acid, HCN, we have 0.0100 mole as well. Now in part B, if we add 0.100 molar sodium hydroxide, we add 100 milliliter of such a strong base into the solution, the amount of the strong base added is also 0.0100 mole. As we just discussed, that we can assume strong acid, a strong base, will react with strong acid first. The reaction is HCl react with sodium hydroxide. Let's put in AQ. This is aqueous solution. It will produce sodium chloride and water. And initially, we have 0.0100 mole of strong acid, 0.0100 mole of strong base. They will react completely to each other. Okay, initially you have 0 mole of salt, and it will generate 0.0100 mole of salt. And in the final reaction, that means we added 100 milliliter of a strong base into this solution. The strong base, strong acid will react completely. And we know that sodium chloride will not impact the pH of the solution at all. So after this, we see in the first part of part B, we see that all the strong acid and strong base will be reacted completely, and the weak acid is left out in the final solution after we add 100 milliliter of the strong base into this 100 milliliter of the mix of the strong acid and weak acid. So in that solution, the volume is 200 milliliter, and we can treat it as a pure solution of weak acid, cyanic acid. It will dissociate partially into proton, H+, and cyanide ions. And we need to recalculate the concentration of a weak acid, cyanic acid. So the concentration is, we have 0.0100 mole, and divided by the final volume, 200.0 milliliter, and converted to liter. And the concentration of weak acid is 0.0500 molar. Initially, we have 0 H+ and 0 C-. Then to reach the equilibrium, now we consider the equilibrium of the dissociation of this weak acid. We assume we need X for H+ and X in terms of the concentration for cyanide, and the concentration of the HCl will decrease by x. At equilibrium, we have 0.0500 minus x, x for H plus, x for C minus. And this x squared over 0.0500 minus x equal to Ka of weak acid, which is 4.9 times 10 to negative 10. Then to judge whether we can approximate x is much smaller than 0.0500, a rule of thumb is we can compare Ka 4.9 times 10 to negative 10 with 0.0500. Just compare the equilibrium constant with initial concentration. We see that 10 to negative 10 is much smaller than 0.0500. So therefore, we can approximate x is much smaller than 0.0500, and 0.500 minus x is about 0.0500. This leading to the equation as x squared over 0.500 equal to Ka equal to 4.9 times 10 to negative 10. We solve this equation, give us x as 4.9 times 10 to the minus 6. And fortunately, 4.9 times 10 to negative 6 is much smaller than 0.0500. Therefore, the approximation we made in here is correct. So this is actually the concentration. 4.9 times 10 to negative 6 is the concentration of H plus. Then we can calculate pH directly. Here we are. Concentration of H plus is 4.9 times 10 to negative 6. pH is negative log 4.9 times 10 to negative 6, which gives us 5.31. That's the answer for the first part of part B.